Let us discuss the energy calculations in simple harmonic motion. When we talk of a simple harmonic motion, the simple harmonic motion, like in case of a simple pendulum, it has got velocity and it has got positions with respect to the mean position. That means it may be here, it may be here, it may be at the extreme position, and because of that position, it has got the potential energy. The energy possessed by a particle by virtue of its position in a field is called as potential energy. Here, as it has got different positions, it has got different potential energies, and the velocity also varies, or being most at the mean position and least at the extreme position. So there is a variation in kinetic energy also. So, body in a simple harmonic motion possesses potential energy due to its position and kinetic energy due to its velocity. Now we are going to calculate and we will talk of the total energy in a simple harmonic motion. That total energy should be conserved. It should not fail the law of conservation of energy. That means the energy at any point should be same. At some point, it may be kinetic. At some point, it may be wholly and solely potential. At some point, it may be sum of potential and kinetic energy. But that sum of potential and kinetic energy should be same everywhere. May it be its mean, may it be its extreme, may it be in between extreme and mean position. Anyway, when we talk of acceleration in simple harmonic motion, that is equal to minus omega square y, where y is its displacement. That means there is an acceleration that is always directed towards the mean position. That means if we are going to lift this body or this bob from the mean position, we have to do work against this restoring force, and the work will be equal to dW will be equal to minus F dy, where F is the restoring force. When we talk of the restoring force F will be equal to m into A, that is minus m omega square y. This m omega square y, we take it as k. That k is equal to spring factor. F is equal to minus k y. Now dW is equal to minus into minus ky into dy. So this is an incremental work. This is incremental work for small incremental displacement of dy when we are lifting it from its mean position. Now to calculate the potential energy, if we lift it or any other force lifts it from the mean position, we have to integrate this equation from 0 to that displacement, and that integration of dW will give us the potential energy. So the potential energy will be equal to integral of dW, that is integral of ky dy from limits 0 to y if we displace it by a distance of y. So the potential energy is equal to integrating this part, k comes out as k is constant and integration of y is y square by 2, so it will be equal to k y square divided by 2 within the limits 0 and y. Putting the limits, so potential energy will be equal to 1 by 2 ky square. The equation of potential energy is then 1 by 2 ky square. If we look at this mean position, at mean position y is equal to 0, displacement is equal to 0, so potential energy is equal to 0. If we look at the extreme position, at extreme position the displacement y is equal to a, so at extreme position the potential energy is equal to 1 by 2 k. Instead of y we will take as a, that is potential energy at extreme position is equal to 1 by 2 ka square. Now talking of the kinetic energy, we know that kinetic energy equation is equal to 1 by 2 mv square. When we talk of SHM, the velocity is equal to a omega cos of omega t, as already discussed. Let the mass of bob be m, so its kinetic energy will be equal to 1 by 2 m a omega cos omega t whole square. That is, kinetic energy is equal to 1 by 2 m a square omega square cos square omega t. Kinetic energy is equal to 1 by 2 m omega square a square cos square omega t. Now this m omega square, as already discussed in potential energy, this is equal to the spring factor K. So kinetic energy is equal to 1 by 2 K A square into cos square omega t. From the knowledge of trigonometry, we know that cos square omega t is 1 minus sine square omega t. So kinetic energy is equal to 1 by 2 Ka square into 1 minus sine square omega t. Now, when we talk of simple harmonic motion, y is equal to a sine of omega t. So sine of omega t is equal to y divided by a. Easy. Now squaring, this is equal to sine square omega t, that will be equal to y square divided by a square. Putting the value of sine square omega t here in this equation, we get kinetic energy is equal to 1 by 2 Ka square into 1 minus y square by a square. Now cross multiplying, that is 1 by 2 Ka square into a square minus y square divided by a square. A square and a square goes. So kinetic energy equals to 1 by 2 Ka a square minus y square. Now, as already discussed, potential energy equals to 1 by 2 Ky square. So the total energy will be equal to addition of the two, 1 by 2 K a square minus y square plus 1 by 2 Ky square. Now simplifying, 1 by 2 Ky square, 1 by 2 Ky square goes, total energy will be equal to 1 by 2 Ka square. Talking about the physical significance of the equations of energy, total energy is equal to 1 by 2 Ka square, potential energy is 1 by 2 Ky square, and kinetic energy is 1 by 2 Ka square minus y square. So if we calculate what is the potential energy at this mean position, as y is equal to 0, potential energy at this mean position is equal to 0. Now kinetic energy at this mean position will be equal to y square is equal to 0, so it is equal to 1 by 2 Ka square. If it is equal to 1 by 2 Ka square, that means total energy is 1 by 2 Ka square. That means at the mean position, the total energy of this simple harmonic oscillator or a pendulum is totally kinetic, and potential energy is equal to 0. Likewise, when we see at extreme position y is equal to a, so kinetic energy as per this equation is equal to 0, and potential energy as this equation, as y is equal to a, potential energy will be equal to 1 by 2 Ka square. The total energy at the extreme position is wholly and solely potential, and total energy at the mean position is wholly and solely kinetic. But the value is never less or more than total energy, that is 1 by 2 Ka square. If we take at this displacement, that is between mean and extreme position, the energy will be partially kinetic and partially potential. If we pull out a graph of the total energy, we will see that this line is total energy, this is the extreme position, this is another extreme position, this is mean position. At extreme position, kinetic energy is equal to 0. It keeps on increasing until it is maximum at the mean position and then goes on decreasing. At extreme position, it is again equal to 0. This curve is the kinetic energy curve. If we talk of the potential energy curve, potential energy is maximum at extreme position, goes on decreasing and is minimum at mean position, and from mean to extreme it goes on increasing and is maximum at extreme position. So this graph is of the potential energy. From the graph it is clear that at extreme position the total energy is wholly and solely potential, and at mean position the total energy is wholly and solely kinetic. If we see between this extreme and mean position, the total energy will be sum of potential energy and kinetic energy. Here it will be sum of this potential energy and this kinetic energy, but its sum will be equal to the total kinetic energy, and that total kinetic energy is 1 by 2 Ka square. Thank you.